Hey, good evening, it's Shelly, and welcome to Saturday Night Statistics with Shelly. This is a video journal entry for Module 11, Multiple Regressions. So, welcome to the Module 11 demo on multiple regressions. I apologize in advance for any background noise you may be hearing as I record this video. My neighbors next door are having a Saturday night celebration. In this module, we will look at two activities. Exercise 1 will look at conducting a standard multi-regression to explore factors that impact people's level of daytime sleepiness. The specific factors we will examine are age, sex, physical fitness, and depression scale scores. And we want to assess how much of the variance and total sleepiness scores is explained by the variables. Are independent variables and which of the variables make a unique significant contribution. So for exercise 1, we are determining how well a set of variables can predict a particular outcome, which calls for multiple regression, and specifically, we're determining how sex, age, physical fitness levels, and depression scores impact levels of daytime sleepiness for people. So our research question is, how do sex, age, fitness, and depression levels affect daytime sleepiness in people, or do they affect daytime sleepiness in people at all? First, we will run multiple regressions in SPSS to collect the data. Specific instructions for doing this can be found on page 159 in Julie Pallant's SPSS Survival Manual. That has been a mainstay for my statistical work all semester long. And in case you are just joining me for the first time this semester, I'll give you a quick overview as to what we're looking at. This video is based on a data set called sleep.save. As you can see right here is a data set from SPSS. And it comes from the Julie Pallant SPSS Survival Manual. It has two views, the data view and the variable view. The data view shows all the responses for questionnaires that people responded to, and the variable view gives question labels, some brief information as to what the question looked like, and the measurement level for how the question was measured. Specifics for what the question answered, if somebody needed more information, could be found in the actual questionnaire. But moving on, I will briefly walk you through the process, but not actually go through the process, because since I've already run it and I have the data present, there's no need in duplicating the data. But for our multi-regression, you would go to Analyze, and then come down here to Regression, and then we would look over here for Linear. You would move your dependent variable from this list of variables. We would find the sleep and association sensation scale, otherwise labeled as total SAS, to our dependent. And this is going to look a little different than we're actually looking at, but this is from the second exercise. I'm not going to go back and change it. For this actual block, which would just look as block 1, you would move your independent variables over here from this list, which would include sex, age, fitness, and depression. And then under the statistics button, you would come through here and select estimates, confidence intervals, model, fit, descriptives, R-squared change, part and partial correlations, collinearity diagnostics. Under the residuals, you would want to make sure that your case-wise diagnostics is checked. and that your outlier's outside radio button is selected with 3 standard deviations. And then you would hit continue. Under your plots, you want to make sure that your Z resid is moved to your Y from this box, and that your Z pred is moved over to X. And you want to make sure under standardized residual plots and that your normal probability plot is also checked, and you would hit continue. And then under save, you would come through and you want to check the Mahalanobis distance and the Cook's distance feature. And then you would hit continue. And you would hit OK. And then when you run the statistic, which I'm not going to do so it doesn't duplicate, you would get quite a bit of information. So it would start right here. And we'll talk about some of this information as the demo goes on. But the first thing we need to do is start checking for assumptions. And I'm just going to briefly show you that over the course of the 2 exercises, we created a lot of information, as you can see. But going back to checking for assumptions, that's part of the 6 steps in hypothesis testing. We obviously already identified and selected the test, which was our multi-regression. But back to assumptions, that includes checking to ensure that our sample size is accurate. It's not recommended to use multi-regressions when you have small samples. Your sample size should be 50 plus 8 times the number of variables, independent variables that you have. And in our case, we have 4 independent variables, so our sample size should be at least 82 participants. We have nothing to worry about there. The number of responses for the variables, as you can see, runs about 225. This first set of tests I did. And knowing that we have more than 200 participants, our sample size is large enough to do a multiple regression. So the next thing we want to check is multi-collinearity and singularity. Multi-collinearity exists when the independent variables are highly correlated with them equaling 0.7 and above. And so looking at our correlations chart created by SPSS here on the left, our correlations as you can see, our correlations, 1 equals a perfect correlation. Our 1.99, age is a negative 1.41. Our fitness is a negative 0.267, and depression is a negative or is a positive 0.482. So multicollinearity does not exist based on the correlations matrix. Next, we're going to test our or check our coefficient chart, which is down here, and we look at the tolerance and the VIF columns. To the furthest right, if a tolerance value is less than 0.10 or a VIF value is above 10, that indicates multicollinearity. In our case, the tolerance values for the independent variables are much higher than 0.10. You can see 0.986, 0.989, as you can see, 0.89, 0.90, and the VIF values are much less than 10. They're all just 1 point something, like 1.014, etc. So we can safely assume that multicollinearity does not exist. So next we need to check for outliers, normality, linearity, homoscedasticity, interdependence of residuals. And to check for these assumptions, we look at the normal probability plot and scatter plot, which comes at the end of our data. So first, let's look. Here's our normal p-plot, and we want to see that our points line up as close to a straight line as possible to indicate no major deviations. Our data points are nearly straight, except for a small section here in the middle. Otherwise, this is pretty much a straight line. So this looks good. And then within the scatter plot, we want our data to be rectangular. In the past, we've wanted our data to show some sort of a curve, but here we want it to be rectangular. So you can actually see that we could create like a rectangular shape with most of our points in the center around the 0. Like I said, you could envision a rectangular around this data, and the data is centered a little more left to the 0, but mostly centered there at the 0. And the outliners would be data points outside negative 3.3 to 3.3. And there are none visible in the scatter plot. You can also use the Mayhall distance and the residual statistics chart by comparing to the critical value provided in the chart 13.1 on page 165 of your text. So let's go to the residual statistic charts. And for our 4 independent variables, our critical value is 18.47. And looking at chart 13.1 in our text, the maximum Mayhall distance was 13.84. So we have not exceeded the critical value. The 13.804 maximum. Here's our minimum. Finally, if Cook's values are greater than 1, there may be a problem, but our Cook's maximum value is 0.075, so that is not greater than 1. Next, we evaluate the model under the model summary value. And we're going to look up here, our model summary value, and check the value under R squared. It's 0.293, and we convert that to a percent, it's 29.3%. This tells us how much of the variance in the dependent variable is explained by the independent variable. So 29.3% of the variance in sleepiness is explained by the model, and to check the statistical significance of the results, we look at the ANOVA table, which is right below, as right here. And our significance is less than 0.001, which means that P is less than 0.0005. So next we evaluate each of the independent variables and we check our coefficients table, which is right here. We look down the significant column right here, and we're looking for values less than 0.05 and they're all less than 0.05, so they're making a significant, unique contribution to the prediction of the dependent variable. And if they were greater than 0.05, then they would not be making a significant contribution. Then look at the part column closer to the right side in the coefficients chart. We then square each value, then convert the value to a percentage to determine the impact of each independent variable separately. So here's where we had our part variable, our numbers, and these are the variables here. So for sex, we took our value, we squared it, converted it to a percentage, and it was 2.4%. Age was 2.1%, fitness was 1.3%, and depression was 16.8%. So to answer our question, what impact do sex, age, fitness, and depression levels, or how do they affect daytime sleepiness in people? The independent variables, sex, age, fitness, and depression have a 29.3% effect on variance of daytime sleepiness, with depression levels making the biggest single impact at 16.8%. For the second assignment in this module, we repeat the same analysis, except this time we're going to control a couple of the variables, age and sex. And so to do this, we're still using a multiple regression, but it's a hierarchical multiple regression procedure. So to do this, we follow basically the same steps minus a few changes. These can be found in the directions on page 196 in Balance Books. I'm going to come back over quickly to the sleep.save dataset. We would go back to analyze. We would come to regression. We would come to linear. Our dependent variable stays the same. And then you'll notice here, this block 2 of 2, if we look, see there was block 1 of 2 and block 2 of 2. The first time we ran our regression, all of the variables were in 1 of 2. And now, being as we have variables in 1 of 2 and variables of 2 and 2, this shows that we are controlling variables in 1 of 2. So by putting sex and age in block 1 of 2, that shows that we are controlling. And in the second independent variable box, we'll put fitness and depression levels. Under statistics, we chose mostly the same topics, leaving off the confidence intervals in the step. And then under the options, we chose missing values, exclude case pairwise, the same thing with plots we did before with standard residual plots that we did before, and also with Mayhall and Cook. Since we already performed the first analysis, we don't have to do all these steps again. Because this is a hierarchical regression, it includes what we did the first time. But then it includes a second step or analysis by isolating or controlling the age and the sex. So we're going to go straight to evaluating the model and then evaluating each of the independent variables. If we were doing this first, or it was the only analysis we were going to do, we would have to go through all of the steps again. But since we've previously explained it, we won't rehash this for time's sake. So under the model for this second multiple regression, under the model summary, we check our values under R square, and our values are 0.00. You'll have to, because you'll have two tables now. So we're going to find them. Model summary. They're 0.060 and 0.293, which means 6% for age and sex. And then 29.3 for all four of the variables, because it runs the same analysis you did before in addition to the one with the controlled variables. So next we're going to look at the R square change column and look at the new graph. Since we didn't do that, in row 2, we have 0.232, which means fitness and depression accounts for an additional 23% of the variance in daytime sleepiness scores. And this is significant. So next we evaluate each of the independent variables. So we check our coefficients table. We look down the significant column for values less than 0.05, and they're all less than 0.05. So they are making a significant and unique contribution to the prediction of dependent variables. And the ANOVA table indicates that scroll back up to it. The ANOVA table indicates that F is 23.258 with P being less than 0.001. So the variables of fitness and depression make a significant impact at 23% on the sleepiness scores, even when sex and age are controlled. If we look at the part column over to the right on our coefficients table, and then we do the same procedure, square the value, convert it to a percentage. We can look at each independent variable separately. Again, sex is 2.4%, age is 2.1%, and fitness is 1.3%, and depression is 16.8%. So depression has the biggest impact on the daytime sleepiness score. And this is the end of our Model 11 demo. Thank you so much for joining us, and until next time, this is all.